Overview of coherence, synchronization, and memory consistency. Nigel. Shared memory model. The shared memory model is one of the process communication mechanism models which are provided by the operating system in order to allow processes to communicate by letting each other know that an event has transpired or that data has been transferred. The shared memory model allows multiple processes to simultaneously communicate. To do this, the communicating processes have to establish a region of shared memory which resides in the address space of the process responsible for creating the shared memory segment. Normally, the processes are not able to access each other's memory since the operating system prevents this. However, if two processes need to communicate, they would need to agree to remove this restriction. Advantages of shared memory model. The shared memory model is faster than the message passing model. Disadvantages of the shared memory model. Processes that use shared memory model address need to make sure that they are not in the same address space. As mentioned before, the operating system normally restricts processes from accessing each other's memory. Therefore, this may cause some problems with synchronization, which needs to be addressed. Hardware components. Computer hardware systems consist of many different types of components. Among those components, some are responsible for inputting data, whereas some are responsible for outputting it. On a circuit board, which is the part of the computer that is responsible for holding everything together, as well as making sure that everything is interconnected, you find many different components. Some components control many different aspects which make a computer function properly, ranging from networking, memory, processors, and more. All of these components are connected through a group of wires which are found in the main circuit board called a bus. One of the main components which you would find on a computer circuit board is a processor, which is also known as a central processing unit, or simply CPU for short. Processors contain millions of small electrical parts. Some even contain billions of transistors. A processor is responsible for performing the main fundamental computation within the system. It is the processor that is responsible for controlling all the other components within a computer directly or indirectly. Coherence and store atomicity with nitrogen. Within a multiprocessor system, many processes require a copy of the same memory block. Maintenance of consistency within these copies creates a problem, which is known as cache coherence problem. This mainly happens because of sharing of writable data, process migration, inconsistency due to inputs and outputs. To solve this, a system has to use cache coherence protocols. Some of the main cache coherence protocols are MSI protocol, MOSI protocol, MESI protocol, MOESI protocol. MSI stands for the possible states in which a cache can be in. MSI is a basic cache coherence protocol used in a multiprocessor system. This protocol can have one of the following possible states. Modified. When data has been modified with inconsistent cache, which does not match the data in the main memory, the cache with the block which has the end state has the responsibility to write the block to the main memory when it is evicted. Shared. The data is present in at least one cache as read-only and is not modified. The data can get evicted by the cache without writing it to the main memory. Invalid. This block is not valid and therefore must be fetched from the main memory or even from another cache in order for it to be stored in this cache. MOSI protocol. This is an extension of MSI protocol which adds the following state in the MSI protocol. Owned, which shows that the present processor owns this block. Only one cache can have the owned state, even though other caches may have the same block. In this case, the other caches must be in the shared state. MESI protocol. This is an extension of the MSI protocol which adds the following state in the MSI protocol. Exclusive. This is when the cache line is exclusively present in the current cache and is clean and its value matches the main memory value. However, it may be changed to modified state when writing it. MOESI protocol. This is a full cache coherence protocol that contains all of the possible states that are mainly used in other protocols. Each of the cache lines is in one of the following states. Modified. The cache line is in the state that contains the most recent and correct copy of data, whereas the copy in the main memory is incorrect, therefore no other processor holds a copy. Owned. The cache line in this state contains the most recent and correct copy of data. This state is like the shared state in the fact that the other processors can hold a copy of the most recent and correct data. However, unlike the shared state, the copy in the main memory could be incorrect. Only one processor can hold data in the owned state, whilst other processors have to be in the shared state. Exclusive. The cache line in the state contains the most recent and correct copy of data. The main memory's copy of data is also the most recent and correct copy of data. However, no other cache line holds a copy of this data. Shared. The cache line in the state contains the most recent and correct copy of data. The other cache lines in the system may also contain copies of data in the shared state also. The main memory's copy also is the most recent and correct copy of data. Only if no other cache line has it in their own state. Invalid. The cache line in this state does not contain a valid copy of data. The valid copy of data could be either in the main memory or in another cache line. Store atomicity. Store atomicity allows us to order instructions. For example, A is to be ordered before instruction B. Serialization is the total ordering of instructions, which essentially means that the local ordering instruction must be respected. Plain coherence. This is when the system enforces a global order of all stores of the same address. This means that the operation of each thread is in the same location and are in thread order. Therefore, the value returned by the by a load is also the value of the latest store to the same location in that serial order. Plain coherence also facilitates the implementation of memory consistency models. This is done by propagating values timely, selectively, and efficiently. Store atomicity and interleaving. In this case, each address is allocated to a separate memory. Threads can therefore issue memory access in any order, which needs to be consistent with their intra-thread dependencies and also with possible orders enforced. Each memory must respond to each request, load, or save one at a time in order for memory addresses to be atomic. However, each thread could have multiple outstanding requests for different memories. Therefore, memories are accessed in parallel by every thread. Thank you.
Hi, I'm Xiaoye Hua. My research topic is about the sequential consistency and synchronization. The sequential consistency is one kind of the memory mode which defined by the Lamport in 1979. According to Lamport's definition, there are two features about the sequential consistency models. The first one is from the view of the entire program. All the processes should work in one designed program. It means that the interleaving orders of the thread execution can be arbitrary, but for each thread there should have one same overall execution order for the entire program. The second one is from the view of one single thread. All the operations in each process should emerge in order designed by this program. This means that the instructions inside each thread are executed in the program order. Let's say three different examples about the sequential consistency. The first one, the example A, is a perfect example which is not only follow the sequential consistency, but also follow the strong consistency. The strong consistency means that at any moment the data in all the nodes should be the same. So in example A, the P1 writes the x equals to 0 first, then the P4 reads the x equals to 0. P2 writes y equal to 2, and P3 read that y equal to 2. So this one is a perfect example for the sequential consistency and the strong consistency. For example B, there is a little bit mistake, but not for the sequential consistency. It's still follow the still consistency, because here's the mistake. The P3 read the x equal to 0, but before that the P2 writes the x equal to 1, but the read x equals to 0, this mistake not only happened in the P3 but also happened in the P4, so it still follows the sequential consistency. And for the example C, the last one is not follow the sequential consistency, because here the P2 writes the x equals to 1 and the P4 read the x equals to 1. After that, the P4 also read the x equals 0, and the P3 also read the x equals 0. This will never happen in the sequential consistency, so this is wrong one. For accessing ordering rules about for the sequential consistencies for each process issues memories or operations in order of the program. For write operations, the process must waiting for the write operations to complete relief to all the process before the issue before to move to the next operations. And for the read operation, the process also need to wait the read operations to complete first, and also need to wait the write operation providing the operation value to be completed for all the processes. After that, it will move to the next memory operation. And about the synchronizations, we have two different. Also have the first one is the hardware-based, and another one is the software-based synchronization. For the hardware-based synchronizations, there's many methods we can use in the hardware. The first one is the interrupt masking, also called the interrupt flag. It will stop the CPU's process. It can be used for the matter interrupts or the single interrupts. And in the interrupt we have the high level and a low level private between different interrupt resource. For example, there is the one level called A, and one level called B, and one level called C. And level A is higher than level B. The level B is higher than level C. When CPU run in the main processing, and level B and level 3 come into at the same times, the CPU will run the level B first. After that, after the level B completed, it will run the level C. And if during the level B or level C is running, there's one level A coming, and the CPU will stop the level B or C immediately and to run the level A. This is the high and low provided means. The second one, hardware-based method, is called the hardware instructions, which including the TS instructions and the swap instructions. First, the TS means the test and the set. Based on this, it's able to read one value from one unit and send this value to another unit. And but the swap is different. Have a different working style. The swap can switch two different values from two different units, and based on the TS and the swap instructions, the CPU's process can make sure it works mutually exclusive. And about the software-based synchronizations, mostly about this synchronization are based on the programming language such as the C, the C++, and the Java. One synchronization is called the mutex lock, which is based on the Java virtual machines. In this lock, the first step is the process will apply for the mutex, just like the process A and process B. It will apply for mutex, and if it's success, it will hold this mutex just like process A. But if the process failed, it will spend the performed, and the process spend to waiting for the mutex online. And continue to apply for the mutex until then gets that mutex. After that, the process will choose the different working modules from the sleeping or the yield, and if the search of the sleeping limit is run off the sleeping limited or is awake active or the completed, it will repeat the first step, just apply for new mutex. Also, we have some other synchronization such as mandatory rotations methods or log the available methods, which include should have the two flags. First, about the log available methods, it has two different types. Which one? This one is called the first check, and another one is called the post check. Most different between these two is the first check will check the flag, the other one's flag first, then set their own flag to true, and then after that send this process into the critical sessions, just like the process 0 and process 1. And about the post check, it will set their flag to true first, then check the flag. The problem of the first check is it might able to make both of this process, the 0 and 1, into the critical session at the same time, into the critical session at the same time, and it will make the mutex field, but the post check will not happen like this. It can make sure the mutex successful, but might make a deadlock about this.
Hi, this is the presentation for the assignment of the Modern Computer Architecture module. In this presentation, I would like to speak about my chosen topic, which is Relaxed Memory Consistency Model. I would also like to briefly mention cache coherence and sequential consistency. First of all, we come to cache coherence. Cache coherence is caching shared data, which causes a problem that two or more computers view the same location or the same source of data, if you like, with different values. And secondly, sequential consistency. Sequential consistency is one of the consistency models which is conservative, and it does not allow any instruction reordering on each core. Although it is an easy model to implement, it still has a weakness or a shortcoming, which is it decreases the potential performance, chiefly in multiprocessors that have huge amount of computers. Relaxed consistency models. The main aim or goal of a relaxed consistency model is to let the read and write operations to complete improperly, but to use a synchronization operation or synchronization operations to enforce ordering, so that the synchronizer program acts as though the processor were sequentially consistent. Relaxed consistency models, they have two types. The first type is weak consistency model, and the second type is release consistency model. And both of these types, they rely on synchronization. In addition to these types, there is a relaxed consistency model which do not rely on synchronization, which I wouldn't be covering in this presentation, as I wasn't able to find enough sources for them. Weak consistency model. Synchronization. In weak consistency model, synchronization accesses are sequentially consistent. Prior to synchronization access can be performed, all former regular data accesses must be completed successfully. In addition, prior to regular access can be performed, all former synchronization accesses must be completed successfully also. The memory in this case will only be consistent immediately after a synchronization operation. The second type, which is release consistency model, this model provides one of the least limiting models that is clearly checkable and ensures that synchronized programs will observe a sequentially consistent execution. This model is built up on the notion that in synchronized programs, an acquire operation must go before an application of shared data, and a release operation must stick to any updates to shared data and go before the time of the next acquire. Also, while many synchronization operations are either acquire or release, some operations such as barrier behaves as both on acquire and release and makes the ordering to be equal to weak ordering. And to recap, cache coherence is caching shared data by cache memory. This lets different processors to view the same location with different values. Consistency models are used by distributed systems such as database systems or file systems. Sequential consistency are relaxed consistency and relaxed consistency are two different memory consistency models. The first one is the most basic model for memory consistency and decreases the potential performance. Nevertheless, the latter one increases the potential performance of the system by allowing the read and write operation to take place inadequately, and then use some synchronization operations to impose orderings so that a synchronized program behaves as if it was sequentially consistent. Relaxed memory models are of two types. One type relies on synchronization and the other type does not rely on synchronization. Those models that rely on synchronization are weak consistency and release consistency models.
Hello and welcome to this presentation of conservative memory model enforced in out-of-order processes. Right, so what are we dealing here with? We are dealing with system performance latencies, where multiprocessors have to wait to perform a process, which slows down the processor and memory use up on the processors. So this happens on memory distribution among processors. Now, why is it a concern? It's a concern because we need improved processor performance. So then we have to find a way around improving this. So the background information in this is what we're looking at is out of order execution. So what is out of order execution? Right. So in a memory consistent model, which is defined as ordering of memory operations on a shared memory or multiprocessor and a multi-core system. So, sequential consistency model forces memory to operate memory operations to be viewed by all processors at the same global order, and its most restrictive memory consistency model. So, for to implement a sequential consistency requires that each memory to be delayed until the previous access in the same process is complete. So that imposes a minimum memory order on the multiprocessors. So the system performance is greatly affected by this because it does not allow overlapping of memory access, which means a process has to complete and be written back to memory before the next operation can happen. So this causes latencies due to distribution of processes and memory. So out of order is a technique that is used to reorder requests to improve performance while guaranteeing same effect as it would be if the request were executed sequentially. So even though the execution happens on an out of order way, the final process happens as if it happens sequentially. So implementing the sequential consistency requires that each memory to be delayed. Now, for high performance processes to be implemented, out of order instructions are executed. Out of order is a technique that will be applied to this process. So there are three kind of out of order that I'm going to talk about here. One is true dependency, and a true dependency is where an instruction needs to read a resource that prior instructions have written. So this is a read after write dependency. And then we have anti-dependency, that is when an instruction writes a resource that a prior instruction needs to read, which is a write after read dependency. Output dependency, on the other hand, is when an instruction write a resource without reading between them. So which is a write after write dependency. So now, while the out of order execution happens, the execution uses a reorder buffer, which tracks the instructions that are in flight or happening with the aim of recovering the machine state in case of an exception. So if a process fails in between and the read and write doesn't happen, and then for instance for the anti-true dependency, if the write hasn't happened, then obviously the read won't happen. So then the process would fall, and then the reorder buffer will help to track the instructions, which means that the process the machine state will be recovered because it will reverse the process. So the conservative memory model enforces enforcement in all processes. So the speculative process order is enforced as a load and store cannot happen until they are ready to commit and retire. So so once the process happens, then load is not bound until it reaches the top of the reorder buffer, where a store and synchronization updates the memory, after which the value cannot be recalled. So after that point, then nothing can be recalled back. So for improved performance processes, then there is a prefetch memory block, which blocks memory in L1 as soon as the load address is known. So the prefetch is subjected to coherence protocols, and in exceptions they are dropped. The memory space is blocked. So with this process, so high performance processes implement out of order instructions executions to tolerate long latencies operation and deliver improved performance. So that's the aim of having out of order process enforcement. Thank you and goodbye.
Hey guys, this is Dev, and I'll be presenting for Group 7. So the first topic is the shared memory communication model. So operating systems have processes that have to communicate with each other to synchronize their actions. This is called IPC, or inter-process communication, and it's one of the models of the shared memory communication model. It's the fastest inter-process communication mechanism. So it's where an operating system maps a memory segment in the address space of several processes so that several processes can read or write in that memory segment without calling OS functions. So how does it work? So there's two processes. A process will request a segment of the shared memory by initializing the memory segment to prepare it for use. The process names it so other processes can find it. The process then maps the shared memory in its own address space, therefore it's enlarged by the size of the shared memory. So basically process A has gotten bigger by the size of the shared memory, so it's mapped it. So finally, processes can read or write from the shared memory freely via common memory, as the shared memory is treated as a local process memory. So an advantage is that memory communication is faster because it's done at memory speeds. Shared memory is also faster compared to the message passing model. It's another type of IPC where processes can read or write data to the message queue without being connected to each other. Another advantage is, from a programmer's point of view, there's no data ownership, so there's no need to specifically or specify explicitly the communication of data between tasks. So all processes can see and have equal access to the shared memory, therefore simplifying program development. Proper synchronization is complex, so manual synchronization is necessary, and failing to do so will result in a race condition where processes access a shared variable at the same time. So it's a programmer's responsibility for synchronization constructs that ensure correct access of global memory. In terms of performance, it's more difficult to manage local data locality. So keeping data local to the processor that works on it conserves memory accesses, cache refreshes, and bus traffic that occurs when processors use the same data. Next topic is hardware components. So a multiprocessor is symmetric when all processors or cores are treated the same on shared resources. So it's only asymmetric when some of them have dedicated peripherals like a memory or a GPU. In a symmetric multiprocessor system, a processor can execute any thread, kernel code, or application code, and this symmetry is achieved through identical processors or interconnects. So this is a symmetric multiprocessor system model, and in a model like this, the main components are the main memory, bus arbiter, cache, and processor. So how does it work? So one of them is a dispatcher. So this sits between the CPU and the dispatcher. So dispatcher gets requests which it assigns to an idle CPU. When it sends a request to an idle CPU, the CPU is marked as busy, and once the request is complete, it's given back to the dispatcher and then given back to the software. So the CPU gets the instruction and decides which require cache accesses, and then requests that number of memory accesses to the cache module. So the cache will respond, and then the CPU will add an instruction delay to take into account the execution time. And once all the instructions are executed, the process is given back to the dispatcher, which gives it back to the software. So a cache decides if a memory request can be filled or if it requires main memory access. So main memory access can be RAM or ROM, and it communicates directly with the CPU. So if main memory access is required, then the request is passed to the bus, and if not, the cache adds a cache access delay and then sends the memory right back to the CPU. So a bus receives and queues the cache fill line, so where the memory then receives the fill request from the bus and then inserts a memory access. So this is sort of like the gateway or the communication lines between from the main memory and to the cache. So it's like the bus arbiter. So speculative violations of memory order is the next topic. So what is pipelining? Pipelining is where multiple instructions are overlapped during the execution. So instructions come from one end and go out the other, and this is known as a static or simple pipeline. So in a few slides we'll look at a 5-stage pipeline where it can do 5 instructions concurrently rather than a simple pipeline where it's just one instruction and one instruction every 5 clock cycles. So in a simple pipeline, instructions are executed in order, and if an instruction is stalled in the pipeline, then no instructions can proceed. So in this example, F sub has F8, which is dependent on Fadd because it has F8. Fadd has F0, which is dependent on Fdiv because it has Fdiv. So F sub can't execute at all because of its dependencies. So this causes the pipeline to stall. So in a 5-stage pipeline, instructions are fetched, decoded, and read in order. So this is the same as a simple pipeline. However, instructions, when they get executed, they wait in something called a reorder buffer, which sits between the execution and where it writes back to memory access. So instructions sit in a ROB, reorder buffer, where they're already executed, but they just wait there with their data ready to write back to the memory access. And as soon as it gets its data, it writes back to register and then retires. So 5-stage pipeline, instructions will take 5 clock cycles to complete. On each clock cycle though, another instruction is fetched to begin its 5 stages. So in clock cycle 1, it starts a new instruction. It's instruction I. In clock cycle 2, it starts another new instruction, but it does the second part, it decodes instruction 1. Instruction or clock cycle 3, it'll do instruction 2, and so on. So speculative execution is used to improve the performance where instructions are executed ahead of knowing when they're required. This can minimize latency and extract greater parallelism. So in a pipeline, the branch predictor calculates which branch is most likely. Basically, the branch predictor tries to predict which branch is most likely to be executed. So let's say there's an if statement, or let's say clocks 5 to 9 is an if statement. So the branch predictor will try and predict which branch is most likely to be picked from the if statement, and it will execute that one beforehand, and if it's picked, it has a high prediction rate anyway, so if it's picked, it's executed quicker because it's stored in a reorder buffer. So it's speculative because CPU could be wrong and execution can be rolled back in the case of an exception. So the last topic is conservative memory model enforcement in out-of-order processors. So when it comes to memory dependence handling and scheduling load instructions to an out-of-order processor, there's a lot of disambiguation problem where younger loads can have its address ready before an older address is known. So there's 3 ways of solving this. A conservative memory model will predict if a load will conflict with any other older stores. The load is stalled until all previous stores have computed their addresses or retired. So it's quite taxing on the CPU, and it also limits the amount of parallelism to exploit. An aggressive approach is to assume that the load is independent of unknown address stores, and to schedule the load right away. So the load will always be scheduled regardless of the number of older stores with unknown addresses. So it's not the best because this can increase the number of mispredictions. However, predictors are getting more intelligent, so it can be a good approach as mispredictions are less occurring. So lastly, it's to speculatively predict if a load conflicts with an early store and delays the scheduling of a load until that store executes. Yeah, so that's an intelligent memory model enforcement. Yeah, thanks for listening.